Roots and radicals. Divide/rationalize. When dividing roots or radicals, the index must be the same in order to divide. I choose to divide what is under the radicals, the radicands, that is, first, and then simplify. All right. However, it's possible to simplify both or either individual radical first, then that is okay as well. All right. Just understand that the radicand from the resulting quotient might need to be further simplified, and or you might need to rationalize the denominator as well. All right. So here's my disclaimer. For purposes of this video, I will assume all variables represent positive values. Please understand that the variables can be negative. So if your book or class does not restrict them, then you must remember the property a squared equals the absolute value of a for any a. All right. You need to remember that. This is actually true for any even root of a variable that results in an odd power. For more info, if negative values of variables are possible, watch my video, Roots and Radicals, Negative Variables. So let's simplify. These are the same index. What's understood to be there if nothing's written there? 2. So you can say this is going to be the square root of 120 divided by 10. They're under the same one. Then I would rather simplify this and then worry about what comes out of the radical at the end. So this is going to be the square root of 12. And then I say, okay, now let me simplify this. 12 is 4 times 3. Why did I pick 4 times 3 and not 6 times 2? Because I cannot take the square root of 6 or 2, remember. I only want to factor radicals into something that is a perfect, in this case, square. So I need 4, 9, 16, 25, remember. So the square root of 4 comes out as a 2, and the 3 stays under the radical. You cannot apply the square root to 3. So the square root of 12 becomes 2 square roots of 3, 2 times the square root of 3. All right, so the next one, they're both under a root with a third, right? Cube root, same index. So I'm going to make one big cube root and do 250 over 2. That's the cube root of 250 divided by 2 is 125. And we remember 5 times 5 is 25 times 5 is 125. So then the cube root of 125 is simply 5. All right? It is simply 5. This can be extended out to variables as well. So let's work this one here that's got numbers and variables in it. Again, they're under the same radical. They're both under a square root. So I'm going to put it under one big square root and say 98 x to the third over 2x. 98 divided by 2 is 49. And x cubed over x, remember we subtract the exponents. 3 minus 1 is 2, so that's x squared. And here again, this is nice because I'm not left with a fraction. If I was left with a fraction, that's okay. I just haven't been so far. The square root of 49 is 7, and the square root of x squared, 2 goes into 2 one time with none left over. Okay? So that's just 7x. And here is where it's important that I assumed my variables were positive. Otherwise, or else I would need an absolute value on that x. But here, since I assumed x represented a positive value, then and actually on this particular problem, I'm okay because this was under here already, so that restricts x domain anyway. X can't be negative or that wouldn't work out. So this problem is actually okay. Works itself out no matter what. Not always the case, but on this one it did. So here, both of them are under a square root. So the square root of c to the 11th, d to the 6th over, let me fix that 6 there, over c cubed d squared. So again, I can subtract the exponents. So really, do I need a fraction? Let's look and see. 11 minus 3 is 8, so c to the 8th and d to the 4th because 6 minus 2 is 4. And both higher powers are in the top, the numerator, so all my denominators divide out. There's just a 1, so I don't need to worry about it. Now I go and say, okay, how does this work? Well, I look at this and I say, how many times does 2 go into 8 for the power of c? So this is going to be c to the 4th. And how many c's are left over? 2 goes into 8 4 times with none left over. No c's under the radical. And then d, 2 goes into 4 2 times with none left over. All right. So then c to the 4th, d squared, and there's nothing left under the radical. It doesn't have to be perfect squares like these, y'all, but I just did some examples that were perfect squares. So look at this one. I'm going to do the same thing for both of them under a square root. This is going to be the square root of 54. That's not 54. Let's try that again. 54 x to the 4th, y to the 8th, over 3x to the negative 3, y to the negative 2. All right, so 54 over 3 is how much? I think that's probably 18. And then I have x to the fourth and x to the third. So what happens is this stays at home because the exponent's positive. But this exponent's negative. It says, hey, move up. That's where the x to the third comes to the top of the numerator. Then y to the eighth stays home, right? Positive exponent. And then y to the negative 2, what does it do? It moves up as well because it is a negative exponent. And it changes from negative 2 to what? Positive 2. Now, one thing that I have not done yet is take my radical, right? So leave the square root there. Students all the time, they do all this algebra under here, and then they go, oh, I'm done, and they forget, I haven't taken the square root yet. Remember, you always have to apply the square root if possible, but first I'm simplifying under here. So there's a little bit more work I need to do right here, just a little bit more work I need to do. I want to take this thing and say, okay, the square root of 18x and y. So here, what do I do with those exponents? I add them. 4 plus 3 is 7. Each exponent has its own power, right? Add them. And then here again, 8 plus 2 is 10. So y to the 10th. And now I'm finally ready. To break this up. Is 18 a perfect square? No, so then I'm going to change it to 9 times 2. And the reason I picked 9 and 2, because the square root of 9 is what? 3. And then I'm going to leave space here in case I bring x's and y's out. The 2 goes under my radical, right? And then here, 2 goes into 7 how many times? 3 times, right? 2 times 3 is 6. So that's 3 times with how many left over? 1 left over, right? 2 times 3 is 6, plus the 1 left over is my 7. That's where I get that from, right? If I do 7 halves, that's 3 and 1/2. It's a mixed number. And then y to the what? 10 divided by 2, or 2 goes into 10 5 times. And how many y's are left over? None, right? Not a single y left over. So we don't put any y's under our radical. So I'm going to clear that up just a little bit. And so 3x cubed, y to the 5th, times the square root of 2x, and that is our final answer here. So again, I wasn't left with a fraction there, but I'm just, again, showing you I'm dividing these things. I promise y'all, it can be left as a fraction. I promise. Just see enough problems in algebra. There'll be some that are fractions and left as fractions and that kind of thing. So here I'm just giving you some that are not. These are both cube roots, so therefore I can divide them under one cube root. So 54x to the 5th, y to the 3rd over 2x cubed. 54 over 2 is 27. X to the 5th over x cubed is x squared. And then y to the 3rd. And this is all under the cube root. So cube root of 27, is 27 a perfect cube? Indeed it is. It just comes out as a 3. Right? That just comes out as a 3 all by itself. There's nothing left under the radical after I do 27. But when I go to x to the 5th, I say, look, I mean x to the squared. I say 3 goes into 2 how many times? It doesn't go into 2. So then under my cube root, and I left space in case I bring any y's out, there's an x squared. I can't bring any of those out. Remember, if the power is not as large as the index, nothing comes out. It's got to be at least as large as the index, and what's left over has to be strictly less than the index. So move that up just a little bit. So we're going to say this is going to be y to the 3rd. So 3 goes into 3 how many times? 1 time. So a y here, and there's no y's left over. So 3y times the cube root of x squared, and that is my final answer for that one. Okay, so the 3 came out, the y cubed came out as a y, 27 came out as a 3 from the cube root, but the x squared could not come out. It could not apply the cube root, so that's why it's still under the cube root there for the x squared. All right? So why is it called rationalizing? Well, because roots and radicals are irrational numbers. Thus, when you eliminate the root or the radical, it becomes what we call a rational number, hence the term rationalizing. The idea of rationalizing is important in math. And I'll guarantee you everybody's going to start screaming, denominator, denominator. Watch what I put here. Oops. The numerator. It's important for what? Say, huh? What are you talking about? This guy's crazy. Mathematically, there is nothing wrong with a root or a radical in the denominator. Say what? Mathematically, there is nothing wrong or incorrect or bad or poor with a root or a radical in the denominator. Nothing at all. So why do we rationalize denominators? Here's why. Before calculators, okay, and by the way, before I say this, let me say, I've had mathematicians, scientists, and engineers who are all older than I am, and I'm getting on up there myself, but I've had all of them older than me who use things called slide rules when they were in school, and these tables of charts and values and things. So before calculators, and they all, by the way, all of them, mathematicians, scientists, and engineers have all told me this story. I've had separate ones tell me this story about rationalizing denominators and logarithms and other things. All right, before calculators, people used tables of values and divided by hand. The long division was much simpler if the root was in the numerator. So if you did not have the square root in the denominator, then the long division that they did by hand using these tables of values was much easier. So somewhere along the way, this became the rule. They just said, look, it's so much easier when the root's in the top in the numerator. Let's just make it a rule. Let's just say you can't have it in the bottom, in the denominator. So calculators have thus eliminated this reason. So now it's basically just because. Just because why? Just because I said so. Just because it's the way it's always been. Just because. Because that's what your book does. Because that's what my teacher did. Okay? And math teachers, we're the worst about this just because. Because we remember, once you learn, it's kind of like riding a bike. Once you learn it, you don't forget it. So, we remember 30 or 40 or whatever years ago when we had it in class. That's why we still say cancel when something divides out, because 30 years ago that was what was taught in books. Now it's not, because it really doesn't cancel. So here it's basically just because, okay? Do we ever need to rationalize the numerator? Yes, okay? It is necessary in the journey through mathematics. In fact, many of you if you're watching this video, you're probably an algebra student trying to figure something out either for Algebra 2 in high school or maybe Algebra 1 possibly, or college algebra, intermediate algebra, something in college. All right, but probably an algebra class, maybe a pre-cal class. All right, but when you get to pre-calculus and talk about limits, or if you get to Cal 1 and talk about limits, so let's just say you're a college algebra student, right? Let's say that you got through math in high school and you made high enough to start in college algebra in college, and you're a first semester college student in college algebra, and you are a business major. You'll take business calculus right after college algebra. There won't be a course in between. And about the third or fourth week in that class, you'll come across a problem that if your teacher chooses to do it, they should, then, or I think they should. How about that? That's subjective. They should. All right. You'll come across a problem where you must rationalize the numerator. It means you've got to put the square root in the bottom or the problem won't work. You got to do what? You got to put the square root in the denominator? I've always taught you can't have. I know. That's because of this right here. This is why we were taught that, all right? Because it's just because I said so now, basically. Because it used to be that way. It used to be better that way, and somewhere along the way it became the rule. So if you're an engineering major, let's say you're in college algebra and you're in engineering, you take trig in between and then you jump into calculus after that. So you're just 2 semesters away from having to put the radical in the bottom for the problem to work in the denominator. All right. So I have seen that. I have seen problems. I have taught them many, many times. I've taught all 4 calculuses and beyond that course, DE, differential equations, some other things along the way. I've taught those things many times. And each time we have to put the radical in the bottom or the problem won't work for a few problems, okay? Never have I run across a problem where I could not, where I had to move the radical to the top. Have never seen it. Now, it may exist and I may just not have worked it. It may be in my current calculus book. I just haven't seen it, haven't run across it. But I have where you have to rationalize the numerator, all right? So, how do we rationalize square roots? For denominators with only one term, okay? That is or contains a square root, you would multiply the numerator and the denominator by the square root from the denominator. All right. For denominators with 2 terms, where either term is or contains a square root, or both terms are or contain a square root, you multiply the numerator and denominator by the conjugate. Okay. So the conjugate is basically copy the denominator but change one of the signs, the sign of one of the terms. Typically, it's the sign in between. So, for instance, if we have 3 minus 2i, then the conjugate is 3 plus 2i. Okay. That's basically the conjugate. So if we want to rationalize a square root, multiply the top and the bottom, the numerator and denominator by the one term. If it's one term, if it's 2 terms, the conjugate. Okay, those are the 2 rationalization things I'm going to focus on here. All right, in this video. If you move to higher order roots, you have to have more than 2 terms in the denominator. Then that is beyond this video. The basic idea is to make the radicand a perfect. That's a blank, like square, cube, 4th power, whatever. So that when you apply the root, it simplifies to something that is no longer under the radical. All right. For example, if you're applying a cube root, you want a perfect cube for the radicand so that when you apply it, it is gone. So let's rationalize the denominator, and let's do a few of these just for practice. Again, I'm doing this mainly because if you're watching this video, you're probably watching it because you have to rationalize a denominator somewhere. Your teacher doesn't share my disdain for this, I guess. Okay, I don't make my students in any class beyond I make them do it in algebra, and that's because if they have another teacher later on that requires them to do it, they need to know how, or if they see it somewhere, they need to know why it is. But I do it to teach them because of numerator, and also in my upper level classes, just in trig, calculus, any of those things, I do not make my students rationalize ever, not a single problem, not once, except when they have to for the numerator to make the problem work. Never do I ask for a denominator to be rationalized. Never in my 22 years of teaching. Okay, have I done it? And I won't do it now. Outside of in algebra where I say, okay, just do this to practice this process because some people think it's important. All right, but it is for the numerator, not the denominator. So here, one term. The one term. So that means we multiply the numerator and denominator by that one term, the square root of 2. Okay, don't go crossing these out somehow or something, because then you're just defeating the purpose. Don't go dividing that out. Just say the square root of 7 times the square root of 2. They're both under the same radical, so that's the square root of 14. If they were not under the same radical, you'd have to leave them separated, but they're under the same radical. Square root of 14 over the square root of 2 times the square root of 2. Look, the whole purpose is because it's just going to be 2. It's the square root of 4. They're under the same radical, but then that simplifies to 2. When you multiply the square root of something times the square root of something, you get something. The radical's gone. All right? Especially when it's a positive number like 2, you don't have to worry about negatives or absolute values or anything. It's just there, boom. And the square root of 14 will not simplify. There's no perfect square that divides into that, so that problem there is finished. Okay, done, completed. So then the next one, square root of 5 over x. And if you notice the whole thing, don't write it this. If you write this, I mean, what did you just write? Especially if your square root does that. Are you talking about the square root of 5, the square root of the whole thing? I mean, right? So be very particular about how you write it. That whole thing is under the radical, and it's very clear. So what I'm going to do is I'm going to break it up into square root of 5 over square root of x, and then multiply that by my single term in my denominator, the square root of x over the square root of x. And so here, square root of 5x, they're both under a radical, over the square root of x times square root of x is just x. And here, even if I didn't restrict it to positive only, this is already an x under a radical with a positive number above it. So that x must be positive or that thing doesn't even work to begin with. So even if I didn't restrict it here, I wouldn't have to worry about it. But if you take the even root and get an odd power, okay, many times the absolute value is required there. So here it's not because I assumed it was positive, and in this case, I just told you it didn't matter anyway because it would have worked out. So 15 over the square root of 3m. Again, this is one term. It's two factors, but one term. So I'll multiply this by the one term. Square root of 3m, square root of 3m. All right? So 15 square roots of 3m over 3m and 3m both multiplied under a radical give me 3m. Now the one extra step here is what? I noticed that, wait a minute, this 15 and this 3 divide out as long as it's one term over one term. This is still all one term. There's no plus or minus to separate it. That's still one term. So 15 over 3 becomes 5 over 1. And this becomes 5 square roots of 3m over 1m, which is just m. So there is your final answer for that one. All right? So this is rationalizing the denominator. Let's look at some more rationalizing denominators. And here, how many terms do I have? I have 2 terms, right? That plus separates that square root of 6 from that 1, right? So it's the square root of 6 is one term and the plus 1 is the second term. So when that's the case, I said we multiply this by the conjugate, square root of 6 minus 1, square root of 6 minus 1. We change one sign, and we typically change the sign between the two terms. But you can do negative square root of 6 plus 1. It doesn't matter. Change one of the signs. So then this is going to be 20 times the square root of 6 minus 1. And I like to leave this factored up here, because when I simplify this down here, it may turn into 20, and then the 20s divide out, or it may turn into 15, and 20 and 15 has something in common, or maybe 10 or 2 or something. So I just want to make sure and see what happens here. So when I FOIL down here, right, this is first, outer, inner, last. The whole reason I use the conjugate. The square root of 6 times the square root of 6 is 6. And then I get the square root of 6 times negative 1, which is minus square root of 6. And then for this part, I get what? The square root of 1 times the square root of 6, which is plus the square root of 6. And then I get positive 1 times negative 1 is minus 1. But these two terms here with the radical, if you use a conjugate, if you multiply by the conjugate, what always happens, or the middle terms cancel. Minus square root of 6 plus square root of 6 cancels. If you want to remember that and just do what they call in the formula a squared minus b squared, just square the square root minus the next thing squared, or square the first term minus the second term squared when you use a conjugate, that always works out. So this becomes 6 minus 1 in the denominator, right? So I'm just going to write that down. Extra step here. All right, so that's going to be 20 square root of 6 minus 1 over 6 minus 1 is 5. Notice I can't put these together right here because one of them's under a radical and one of them's not. They're not like terms, okay? So, but the 20 is factored out. This 20 is times all this stuff. That's why I left it factored. If I had this, then I couldn't cross that out. That's a no-no. That's a no-no. Can't do that. So here, because the 20 is still factored out, I can divide this out, and I'm left with a 4 here and a 1 here, which is nice because now I don't have a fraction anymore. Okay, I'm simply left with 4 times the square root of 6 minus 1. I'm okay with this answer right here, but just know sometimes your teachers want you to go ahead and distribute that, or your book or whatever. So here's an alternative answer here. So if you were in my class, I would actually take either one of those answers, but I would prefer the top answer. You leave it factored 4 times that. Why not? Okay, but either's fine. Either one of those is just fine and dandy. All right. So let's look at another two-term denominator. Square root of 10 minus the square root of 3. Notice the 10 is under the radical, but not the minus, right? And not the next. The radical over the 10 does not extend out over the square root of 3 or the negative, okay? And those are things in math where that happens. Not just the negative, but the whole rest of it. But here it stops. Square root of 10, stop. Minus square root of 3, stop, okay? And that's all the denominator under 17. So it's two terms. So I multiply by the square root of 10 and the square root of 3, and I change from a minus to a plus. A minus to a plus, okay? So this is going to be 17 times the square root of 10 plus the square root of 3. And again, I'm going to leave the 17 factored out just in case I get 17 in the denominator, or 34, some multiple of 17 or something that divides out. In the denominator, square root of 10 times square root of 10 is 10. And then I get plus, right, the square root of 30 and minus the square root of 30. They cancel. If you want to write them down, you can, but they're always going to cancel. And then negative square root of 3 times positive square root of 3 is negative. Square root of 3 times square root of 3 is 3. And then I simplify this 10 minus 3 and get what? This is going to be 17 times the square root of 10 plus the square root of 3 over 7. And I love this answer right here. I love it. Okay. I really like this up here better. That's better to me. But anyway, all right. So what's the other thing I can do here? I can distribute this 17, right? So the or answer here, 17 square root of 10 minus 17 square root of 3, and that's not minus, that's plus, over 7. Okay. And here, if you use a slanted fraction without parentheses, it's wrong. Period. You can't argue yourself into making me believe you're right, because you're not. Okay. If you use slanted fraction here and there's no parentheses, it is wrong, 100%. If I do it, I'm wrong. Same thing. Okay. So either way is okay for me. But you want to make sure that you understand what your teacher wishes you to do. All right. If you have someone else. All right. How many terms are in the denominator? 2 again. Right. 2 terms in the denominator again. So I'm going to multiply this thing by the conjugate. So it's going to be the square root of x. And then it's going to be minus 2. And notice it's not this. That's something totally different. Don't put that minus 2 under the radical. The square root only contains the x. It only goes over the x, not the minus, not the 2. All right? So now I'm going to leave this as going to be 3 and then the square root of x minus 2 over square root of x times square root of x when our FOIL is x, and then we get minus 2 of those, plus 2 of those cancels, and then a plus 2 times a minus 2 is minus 4. And look, x minus 4, this doesn't even simplify. So there's no way for the 3 to divide out. So this is actually a great answer, or you guessed it, I can distribute the 3 and get what? 3 square roots of x minus 6 over x minus 4. That's fine too. I prefer the factored answer over here because this tells me I factored it and I know nothing else divides out, so I'm good. Actually, I prefer this right here, but anyway, okay. You figured that out by now, all right? Rationalize the numerator. This right here, this is actually contained, the book that I currently teach calculus out of has H here. So this actually is part of the problem that I do about the 3rd week of class, maybe the 4th week, somewhere in the first month of school. I do this to where if we don't do this way, it doesn't work. Okay? It does not work. All right? I've taught pre-calculus before. If in that class as well, same thing, Cal 1, B-Cal 1, I've taught all 3 of those. Got to do it. Got to do this right here, or it doesn't work. And I've had this exact problem, maybe in a different form, not H, maybe something else, but in a different form where it has to be done this way. So it's the same idea. I have 1 term and 2 terms up here. So it's 2 terms. How do I rationalize something with 2 terms? I take the conjugate, the square root of x plus h, and I do plus the square root of x. The square root of x plus h plus the square root of x. Okay? And then now I'm going to FOIL this. Right? And when I do that, the square root of x plus h times the square root of x plus h is just x plus h. Then we get plus, I'll show it this time, plus x times the square root of x plus h. And then I get minus the square root of x times the square root of x plus h. And then I get minus, say I got a minus times a plus, and the square root of x times square root of x. So that's going to be minus x there. Okay? And this and this cancel, right? Again, we know that because we did a conjugate. Over, I'm going to leave it h times the square root of x plus h plus the square root of x, okay? So now let's simplify. We have in the numerator, in the top, we have x plus h minus x over h times the square root of x plus h plus the square root of x. And notice x plus h is the only thing under the radical, and then plus square root of x is after that. And it's clearly that way. Here, let's see what happens here. X and minus x cancels, right? And I'm left with just good old h. And that does cancel, by the way, because it goes to what? 0. It does indeed cancel. Plus the square root of x. And then here, these h's divide out. That's what I mentioned earlier, that 30 years ago, every book, every teacher said cancel. 30 years later, a lot of teachers still say cancel. No book says cancel. All right? So it doesn't cancel. That's why if you look it up in the dictionary, you're going to see that it does. That's because the math people, we lied to the dictionary so long they believed this. Merriam-Webster believed this, and they wrote it down in their dictionary. Okay? So it really divides out. So this is going to be 1 over the square root of x plus h plus the square root of x. And that's what that simplifies down to. And the only way for this problem to work in those pre-calculus and Cal 1 and B-Cal 1 that I'm talking about, business Cal 1, is to do this right here. It doesn't work any other way. Okay? It just goes bonkers. All right? And it's because we do something with this h and we say it has to be 0, and we know from algebra that we can't divide by 0, right? So we have to manipulate it somehow, and this is how we have to do it. It must be done this way or we can't do it. All right? So I hope this helps with dividing radicals and roots, and also with rationalizing, because you probably have to do it even though rationalizing the denominator is just something that we do just because. All right, so I know I'm going to get lots of nasty messages from teachers about that, but I mean, just look up the history of it and talk to somebody older than you that had to use these tables of values. All right, they'll tell you it's true.